Well, we've made it. This is our final mini lecture in the unit. So let's do something fun. Let's talk about black holes. As we mentioned in the last mini lecture, black holes are formed at the center of a supernova explosion when a star collapses inward on itself. But to understand what a black hole is, we need to leave stars for a minute and go back to talk about gravity. So if I toss something up in the air, it'll go up and come back down. And if I toss it faster, it'll go further and before it comes back down. And if I throw it fast enough, it would actually go all the way around the Earth and come back around. And we call that orbit. So here's a picture. Let's imagine that we have a giant mesa in the Himalayas, it looks like. And for some reason, on top of that mesa, we put a big cannon. And the cannon can shoot a cannonball at about 7 kilometers a second. If we do that, the cannonball will begin to fall to the Earth, but it's moving forward so fast that as it begins to fall, the Earth curves away underneath it. And so the ball will go the entire way around the Earth and come back and hit the back of the cannon, which isn't necessarily a smart thing to do, but that's what happened. Now, if we shoot the cannonball a little faster, the cannonball will fall slower than the Earth's curving away from it, and so it gets a little further away from the Earth, but eventually gravity brings it back around, and this orbit again would come back and hit the back of the cannon. So, depending on the speed at which we fire something, the cannonball can either fall to the ground or orbit the Earth. If we shoot it fast enough, and for the Earth it's about 11 kilometers a second, really 11.7 kilometers a second, the cannonball will go off and the Earth's gravity will not be able to pull the cannonball back. It will escape into space and never return to the Earth. That's what we call the escape velocity. So the escape velocity for an object is how fast you have to be moving so that you leave its gravity and gravity won't pull you back. And the escape velocity depends on both the mass of the object and the size of the object. So the Earth is about 8,000 miles across. It has a pretty big mass. You have to be going at 11.7 kilometers a second, several miles a second, to leave the Earth and never come back. The moon is smaller than the Earth. It has less mass than the Earth, and so you don't have to go nearly as fast to leave the moon's gravity and never return to the moon, 2.4 kilometers a second. The sun's a lot more massive than the Earth, a lot bigger than the Earth, and for the sun you need to be going at 630 kilometers a second to leave it and never come back, at least if you were standing on the sun. Now if we go the other way, Halley's Comet, comets are just a few miles across. They're made mostly out of ice, so a few miles of ice does not have a strong gravity. And for Halley's Comet, you would need to be moving at only 5.1 feet per second. That's 3.5 miles per hour. So if you went for a brisk walk on Halley's Comet, you'd leave it, you'd fall off it and never come back. So keep that in mind. If you're ever walking on comets, a slow shuffle is all you want to do. Now, as I said, the escape velocity depends on both the mass of the object and the size. The more massive it is, the faster the escape velocity. The smaller it is, the faster the escape velocity. So you have to worry about this combination of the two. So let's take the sun. The sun's escape velocity is 630 kilometers a second. If we were to shrink the sun in size, that escape velocity would become higher. You'd have to be going faster to leave the sun and never come back. Continue shrinking the sun, keeping it the same mass, smaller and smaller and smaller, and if we were to shrink the sun down so that all of its mass were in a ball only 3 kilometers in radius, so about 3 miles across, then the escape velocity of the sun would be the speed of light. In other words, since nothing can go faster than the speed of light, there would be nothing that could escape the sun, not even light itself could escape the sun and not be pulled back by gravity. So since nothing can escape an object like this, not even light, we would call it a black hole. And the size of a black hole is how close you would have to be before you would cross this horizon we call the event horizon, where if you're closer to the black hole than that, 3 kilometers for the sun, you would never be able to get out. Not even radio waves could get out to tell other people to call for help. If you're further away than that, then light can escape, and so if you were orbiting the black hole, you would be able to radio away for help. Whether or not they could help you is a completely different matter. So if you have more mass, you don't need to shrink it quite as much to make a black hole. So a star 10 times the mass of the Sun, if we shrank it to a black hole, it would be 30 kilometers across. The Earth, if we wanted to turn the Earth into a black hole, we'd have to shrink it until it was just half an inch across, 1 centimeter. So just like anything else, the further away you are from a black hole, the weaker gravity is. And so if you replaced the Sun with a black hole that had the same mass as the Sun, by the time you got out to Earth's orbit, the gravity we would feel from this black hole with the same mass as the Sun would be exactly the same as the gravity we feel from the Sun itself. The mass is the same, our distance is the same, the force of gravity only depends on the mass and the distance. So if we replace the Sun with a black hole, the Earth would continue to orbit around just like it does now. In fact, all the planets would continue to orbit around just as they do now. The weird stuff for black holes only happens when you're really close to this event horizon, say 10 times the size of the black hole. So the black hole Sun would be 3 kilometers across. If you are closer than 30 kilometers, weird stuff will happen. If you're further away than 30 kilometers, then gravity would seem pretty normal. You could orbit around it, you wouldn't get sucked in or anything like that. Nothing weird would be going on. So in other words, black holes are not vacuum cleaners. They can't pull stuff in from large distances. Things only fall in if they get closer than maybe 10 times the size of the black hole. So a black hole is not a Dyson. As one of my professors told me, black holes do not suck. Physics does, math does, black holes don't. Think of someone you don't like, and you take them on a journey to a black hole, and when you get close to this event horizon, you decide to push them in. So they fall into the black hole, and you listen to them over the radio as they fall in. So the strength of gravity, as we've already said, depends on distance, and if you get close to the surface of a black hole, the gravitational field at your feet will be stronger than the gravitational pull on your head. So your feet get pulled in faster than your head, which means you get stretched out. And in fact, what would basically happen is this force of gravity that's different would stretch you out into a long string of atoms. Meanwhile, from side to side, black holes also squeeze space and time, so you get squeezed inward as you're pulled out long. We call this process spaghettification. That's the actual scientific term. So you become basically a long stream of atoms falling into the black hole, or more to the point, the person you pushed in does. Up until the point where the person crosses this event horizon. The event horizon is the edge of the black hole. So for the Sun, the event horizon would be 3 kilometers from the center. Up until the point when the person you've pushed into the black hole crosses this event horizon, they could still send out radio waves or light beams to let you know what was happening. But as soon as they cross that event horizon, not even light can escape. So once they cross it, they can't radio out to tell what's happening. So what happens in a black hole stays in a black hole. So you get stretched out like this, they try and radio for help, the radio wave goes out and is pulled back into the center of the black hole. We call that center of the black hole a singularity because we think that all the mass, everything that falls into a black hole, is compressed into an infinitely small point at the center of the black hole. Although honestly, we don't know what happens inside a black hole because whatever's going on inside this event horizon, light from that, which is the fastest thing, cannot get out to tell us. So maybe there's not a singularity in there. Maybe you fall into a black hole and there's a wormhole to some other dimension, or maybe you get inside a black hole and all the other stuff that's fallen in there is sitting around having a tea party, and you can sit and have a tea party too. We just don't know. So one of the questions we astronomers get asked is, well, if light can escape from a black hole, how can we detect them? Well, the way we detect them is from stuff that is falling toward the black hole but hasn't yet crossed this event horizon. So here's a artist picture of a black hole called Cygnus XR-1. This black hole is swallowing gas from a neighboring star, and that gas, as it goes into the black hole, spirals around and it makes a disk. This disk, the gas particles are bumping into each other, and so they heat up as they fall in. And as we've already learned, and we've talked about many times, as stuff heats up, it begins to glow. And the hotter it is, the shorter the wavelength at which it's glowing. And so as this gas falls in, it will get hotter and hotter and hotter, and glowing at shorter and shorter wavelengths. So it may glow at radio wavelengths far away, optical wavelengths as it gets close, and even up to X-ray wavelengths right before it falls into the event horizon. And so we can see that light. That light can escape, but once the gas falls into the event horizon, we no longer see any light from it. So this gas that's orbiting Cygnus X1 and other black holes, it will heat up, it will glow. We can see the gas. We can use the Doppler shift to measure the speed of the gas. And because we can measure the speed of the gas, we know how fast it's spiraling, how long it takes to go around. This lets us measure the strength of gravity, so we can measure the mass of what it's falling onto. And we can learn quite a bit about a black hole, even though once stuff falls into the black hole itself, it vanishes. This is how we detect black holes. This is how we've been able to prove that they exist. Another way of proving that black holes exist can come from watching the center of our galaxy. There's a large black hole at the center of our galaxy. We believe it's at a point that's coincident with a radio source called Sagittarius A star. Again, long story how it gets that name, but Sagittarius A star is a radio source. We think it's a big black hole, several million times the mass of the Sun, and astronomers have been able to watch stars near this black hole. And this is a movie of these stars taken in infrared light. So the infrared light can reach us from the center of the galaxy. And over about 20 years here, you can see stars actually orbiting the center of the galaxy. But notice something. The point that they're orbiting about, that little star at the center marks the center of our galaxy, there's nothing visible there. There is no infrared light from that point, but yet we see the stars going around it. So there's got to be something there. If we measure how fast the stars are going, and this is a complicated diagram, don't worry too much about it, but basically if we measure how fast the stars are going, we know how much matter must be there. And these stars that are near the center of the black hole, as we get closer and closer to the center of the galaxy, we see that there's a flat amount of material there. That there is about 2 to 4 million times the mass of the Sun in a region that is smaller than our solar system. The only thing we know of that has that much material, that can have 2 million times the mass of the Sun in something smaller than our solar system, is a black hole. And we call this a supermassive black hole because while a single star can make a black hole that's 5 or 10 times the mass of the Sun, this one is 2 to 4 million times the mass of the Sun. And we still argue about how these formed. Were there maybe a million really massive stars at the center of our galaxy that after they made black holes, those all merged together? It's possible. Or maybe a few black holes formed at the center of our galaxy, and then gas from further out was pushed in by gravity, by the gravitational pull of these stars orbiting around, and the black hole swallowed that and grew. It's really difficult to say. So we don't know where these supermassive black holes come from, but we do see them in the center of almost every single galaxy in the universe. We see the same thing, stars or gas orbiting something that otherwise is not emitting light, and the only thing that it can be is a black hole of 1 million to even, in one case, 10 billion times the mass of our Sun. So here's a summary of the life cycle of stars. Stars that are low mass, like the Sun, they become a red giant, a planetary nebula, and then on to a white dwarf. Stars that are much higher mass than the Sun, well, they start off kind of blue, they'll become a red giant, and then they'll explode and leave behind either a neutron star or a black hole. And the outer material gets recycled in the galaxy. The black hole or the neutron star or the white dwarf just hangs around. They continue to exist. Every white dwarf, every neutron star, every black hole that's ever been made in our galaxy is still out there somewhere. Sometimes they're hard to see, sometimes they're easy to see. Depends what's around it.